Okay, now you should recognize this screen from the prior mini lecture when we conducted the one sample difference of means test, testing whether the average amount of soft drink beverage consumed by college students was about 120 ounces. Recall from that first mini lecture on this data that I indicated that we had data on gender, but we actually ignored that. We did not take into consideration at all the fact that we had data on males and females. So we now move from the one sample difference of means test to the two sample difference of means test. And what we do here is we partition our data into two groups. We have a group of males and we have a group of females. Now I happen to set this data file up to where we have 10 males and 10 females. I want to emphasize it's not necessary for our sample sizes to be equal to one another. It just happened to work out that way. So all I did to create this particular data set here was I copied the amount of beverage consumed by each of the 10 males into this column and the amount of beverage consumed by each of the 10 females into this column. And if you will recall, on the previous difference of means test, the average amount of carbonated beverage consumed by the 20 students in the aggregate was 123 ounces. But now what you'll see is while the overall average may be 120 ounces, men in this study only consumed 94 ounces per week of carbonated beverage, while women drank 153 ounces. So we have two groups, and we want to ascertain whether the average amount of carbonated beverage drunk by men is equal to, greater than, or less than the average amount of carbonated beverage consumed by women. Without even doing the difference of means test here, it seems kind of obvious to me that women drink more carbonated beverages than men. In fact, from this data here, you can say it looks like women drink about 50% more carbonated beverages per week than men. Nevertheless, we'll go through the mechanics of the difference of means test, partly so that we can look at the computer output, and partly so that we can learn something about the impact of sample size on p-values. So what we'll do now is we will conduct a two-group difference of means test on this data. So we first click on add-ins right here. And we then go over to Megastat and we click on Megastat. We drag down to hypothesis tests. And in this instance, notice how I drag down then to compare two independent groups. I should mention that we know these groups are independent of one another because by definition, if you're male, you can't be categorized as female, and if you're female, you cannot be categorized as male. So these groups are mutually exclusive or independent of one another. Okay, so we click on the compare two independent groups, and you notice here we have our screen for data input. It asks for where is group 1 data located, where is group 2 data located. So I'll highlight the column header for males along with all 10 observations for group 1. Actually, I'm going to change that. I'm going to consider females to be group 1. Notice I highlighted the column header female as well. I click in the box for group 2 and I designate the male data there. You'll see momentarily why I decided to do that. Now, our hypothesized difference is 0. We run the t-test because of our small sample size. Late in this semester, if time permits, I'll explain to you the difference between pooled variance and the unequal variance. That's irrelevant to us at this point in time. So we'll stick with the pooled variance for the t-test. 95% confidence interval, I'll not dwell on that, but I will ask for the data corresponding to that. And I set this up as a two-tail alternative because prior to collecting the data, we had no reason to think that men might drink more carbonated beverages than women, or that women might drink more carbonated beverages than men. So we now have all the data into our input screen, correct? So we just click on OK to see the output. And there's the results. The first thing that you'll notice is that our descriptive statistics here exactly match what I reported on the previous screen, average of 153 ounces for women and 94 ounces for men. Now, if you'll recall, I decided to set women up as group number 1 and men up as group number 2. That was only so that my difference value here would be a positive number rather than a negative number. It just makes the calculations a little bit easier. Okay, doesn't change the statistics at all. It just makes explanation of things a little bit easier. For the moment, I'm going to skip over this portion of the output. I'll come to that another time. But here now we will focus on our t-value and our p-value, okay? And recall, as I said earlier, that Megastat does not provide the critical t-value, so we have to look that up ourselves. So on page 377 in the textbook, for 18 degrees of freedom, you'll see that the critical t-value is 2.101. So let me just type that in here, 2.101. And then also recall that our critical p-value is 0.05. Remember, 0.05 just means we're willing to tolerate a 5% possibility of a type 1 error. So to decide whether to reject or fail to reject the null hypothesis, our observed t of 1.194 is less than our critical t of 2.101. So when your observed t is less than your critical t, you fail to reject the null hypothesis. As it pertains to the p-value, our observed p-value is 0.2479, which is significantly larger than our critical p-value of 0.05. With the p-value, when your observed p is greater than your critical p, you fail to reject the null hypothesis. So based on inspection of our observed and critical t-values, we fail to reject the null hypothesis. Based on inspection of our observed and critical p-values, we fail to reject the null hypothesis. I remind you that we will never get conflicting answers between the t and the p. We always draw the same conclusion. And that's why once we get through the computational phase of this class and we strictly rely upon Megastat output, we'll just look at the observed p-value and based on that decide whether to reject the null or fail to reject the null. So if you think what happens here, we have a huge difference between the amount of beverage consumed by the males and females in our sample of 10 each. It seems obvious that women drink more than men, yet based on our p-value, or t for that matter, but based on our p-value here, we fail to reject the null hypothesis, and therefore we conclude that men and women drink the same amount of carbonated beverage. How could that be? Has inferential statistics betrayed us? Okay. Well, the reason for that, you will find, is because we have a small sample size, and it's primarily due to the small sample size, somewhat due to the fact that our variability of the data is large, but primarily it's due to the sample size. Okay? Now, before I move off of this problem here, though, I want to redirect your attention, as I did in the previous mini lecture, to this portion of the output. Our margin of error is 103.802. And again, I expect you to be able to go to really chapter 8 to reaffirm your understanding of what the margin of error is and how to do its computation. It's also addressed in chapter 10. But the margin of error here, which is the critical t-value times our standard deviation divided by the square root of the sample size, our margin of error is 103.802. So if you take our point estimate of 59, and if you subtract our margin of error, 59 minus 103.8 is equal to negative 44.8. And if you take our point estimate of 59, and if you add 103.802, that's how you get the upper bound of our 95% confidence interval of 162.8. So now let's think for a moment managerially, what does this mean? What does this mean? This means that This means that based on the data available, women might drink 44.8, let's say 45.8 ounces of less carbonated beverages than men, or they might drink as much as 163 ounces per week more than men. So our failure to reject the null hypothesis here, which is, again, is contrary to sound logic, okay? But the reason why we fail to reject the null hypothesis, if you will notice, that contained between the lower bound of minus 44.8 and the upper bound of 162.8, contained between those two numbers is the value 0, okay? So we can't rule out the possibility that the difference between men's average consumption and women's average consumption of carbonated beverage per week, given that our lower bound is negative and our upper bound is positive, we cannot rule out the possibility that the difference between men's and women's average consumption of carbonated beverages per week might be 0. And that is why, contrary to what our logic might lead us to conclude, that we're not able to reject the null hypothesis. And why is that? It's because our margin of error is so large that that the upper and lower bounds are actually 200 ounces apart, okay? From minus 44.8 to positive 162, that's more than 200 ounces distance between your lower and upper bounds. So again, we interpreted everything correctly. We set up the problem correctly. We got contrary results here that is primarily attributable to the fact that we have a small sample size, somewhat attributable to large variability in our data, but mostly attributable to the fact that we have a small sample size.